All right, welcome back, everyone. Today we're taking a deep dive into some pretty fascinating stuff. Imagine, right, you're knee-deep in some really gnarly technical problem and just wish you had, like, a fast track to understanding it all. That's kind of what we're aiming for today.
Exactly. You hit the nail on the head.
We've got this gold mine of material. It's from a detailed interview with a technical candidate, and we're going to extract the most valuable, most practical insights on how to handle those tough data challenges, the kind that make you want to pull your hair out, and also how to keep systems running smoothly, without hitting those dreaded slowdowns.
It's like having a backstage pass to the thought processes of someone who really knows their stuff.
Yeah. These,
And what we're going to do is walk you through the complexities of managing data and making sure those systems just hum along nicely. And all of this is based on this real-world technical conversation that honestly was just packed with insights.
Oh, yeah, for sure.
But our promise to you, the listener, is to give you the meat of it all. You know, those aha moments. We don't want to bog you down with too much technical jargon. It's about making it click.
Okay, so let's jump right in. And we're going to start with something super fundamental, like the bedrock of everything, data.
Can't go wrong with that, right?
The interview actually kicks off with this candidate describing how they would approach a data set, right? And imagine, this data set's got all sorts of issues, missing values, crazy outliers, inconsistencies, you name it. And what's so interesting is their very first move is to just get to know the data inside and out, like become best friends with it. And they do this through what's called exploratory data analysis. EDDA for short.
That's always step one, wouldn't you say?
Oh, absolutely. It's like before you clean up a messy room, you got to know what kind of mess you're dealing with, right?
Yeah, you got to assess the damage, see what you're up against.
Exactly. And the candidate actually mentioned using tools like pandas profiling.
Oh, yeah. Pandas profiling is great.
To generate these like super detailed reports, getting all those summary stats. And then on top of that, they visualize the data's distributions, seeing the patterns, using libraries like Seaborn and Matplotlib. And it just makes me think, like, why is this initial exploration so critical? What's the big deal?
I mean, the way I see it, it's all about getting a real grasp on the data's personality, right?
Wow, yeah.
You know, its shape, its quirks, those little hidden problems lurking beneath the surface.
Yeah, those gotchas.
It's like detective work.
Yeah.
And the candidate even mentioned this library called Missing Neo.
Oh, yeah, Missing Neo. That's a good one.
And it's specifically designed to visualize where the data is playing hide and seek, where those missing values are. And what's cool about it is it goes beyond just, counting empty cells. It's about seeing if there's a rhyme or reason to those missing pieces.
Yeah, is there a pattern?
Exactly. And then they touched on this super crucial point, which is understanding the why behind the missing data. Why is it gone? What happened? And that's where those terms they mentioned come in, right? MTRR, MDR, MNAR. It's like trying to piece together the backstory of the data.
Yeah, like what's the story behind these gaps? Did someone accidentally delete something? Is it a systematic issue?
Precisely. Knowing if the missing data is missing completely at random MCR or missing at random MAR, or even missing not at random MNAR, that's huge.
It's a game changer.
Because it tells you which data imputation techniques are actually statistically sound. The ones that won't mess up your analysis.
Right, you don't want to introduce bias because you filled in the blanks the wrong way.
Exactly. And the candidate didn't stop at just labeling the type of missingness. They really stressed the importance of using statistical methods to put those assumptions to the test. And that's where things get even more interesting.
Okay, now you've got my attention. Tell me more about these statistical tests, because the candidate did mention something called Little's MCAR test. It sounds a lot more, I don't know, rigorous than just eyeballing patterns.
Yeah, it's definitely a step up in terms of rigor. And what's insightful here is that Little's MCR test, it doesn't just look at the data, it actually statistically examines whether the missingness is truly independent of both the data you see and the data you don't see.
So it's kind of like, in a crime show where they're checking for fingerprints, but for data, making sure there's no hidden connection to the missing parts.
Exactly. And the way it does this is by comparing how likely your data is if we assume it is MCR. And it uses a chi-squared statistic to crunch the numbers. But, and this is a key thing to keep in mind, is that this test assumed your data follows a multivariate normal distribution.
Okay, so it's a powerful tool, but it's got this condition about the data's distribution.
No,
Got it.
It's a specialized tool, right?
Yeah.
Works great for its intended purpose, but you got to make sure you're using it on the right material.
And the candidate also pointed out that this test isn't very good at sniffing out MA or MAR. So what happens then? What's the next step in the investigation?
Good question. And the candidate, very smartly, brought up the use of tests based on logistic regression. These tests are like a different lens for looking at the data. They help us see if we can predict the missingness in one variable using the other variables we do have. If we can, that hints that we're dealing with M&A.
So it's like finding clues in the existing data to explain why some data went missing.
Exactly. And for those really tricky M&AR situations where the reason the data is missing is actually related to the missing values themselves, well, that's a tough nut to crack. But the candidate had some advanced techniques up their sleeve, like Rubin's tests and the Hausman test, and these tests can delve deeper into that M&AR territory. It really showcases a really comprehensive approach to getting to the bottom of why our data has gone on vacation.
Okay, so now we've spent some time understanding why our data has gone missing, but what about dealing with it, filling in those gaps? The candidate talked about context-dependent imputation strategies, and that makes a lot of sense, right? I mean, you wouldn't fill in a missing temperature reading the same way you'd handle a missing customer name, would you?
Absolutely not. Each type of data needs its own special treatment. And the candidate gave us a really practical breakdown based on, what kind of data we're dealing with. So for numerical data, they mentioned mean imputation.
Oh, that's a classic. Nice and simple.
It is, and it's perfectly fine for cases where the data is normally distributed and we think it's missing at random. It's a straightforward way to fill in those blanks. But they also brought up a more, I guess you could say, sophisticated technique called MIE.
MCAR, what's that stand for?
It stands for multiple imputation by chained equations.
Ah, okay. That makes sense.
And they specifically mentioned using it with Bayesian ridge regression for those cases where things are a bit more complex. Now, what's really cool about MIC is that it actually takes into account the uncertainty we have about those imputed values. It doesn't just give you one answer. It creates multiple plausible versions of your data set, each with slightly different imputed values.
Oh, that's interesting. So it's like giving you a range of possibilities instead of just one definitive answer.
It is. It acknowledges that we don't know for sure what those missing values should be. And then moving on to categorical data, they mentioned mode imputation. That's where you use the most frequent category to fill in the gaps. And also k-nearest neighbors imputation, or KNN.
Ah, KNN. That's a good one for finding similar items.
It is. And in this case, it looks at the most similar data points to try and figure out what that missing value should be. And this approach can be a lot better at preserving those relationships within the categorical data.
Yeah, it's like trying to match the missing puzzle piece based on the pieces around it.
Exactly. And finally, for time series data, they talked about forward fill or backward fill. But, and this is a big but, they emphasize that you got to confirm stationarity first.
Okay, now you're getting into the technical weeds a bit. What does stationarity mean?
Good point. Stationarity basically means that the statistical properties of your time series, they don't change over time. Think of it like a steady heartbeat. And that's important because if your data isn't stationary, those simple forward fill and backward fill methods, they might not be reliable.
So it's like, you can't just assume things will stay the same over time. You got to check.
You got to check. And what really stood out to me was their mention of using domain knowledge to set thresholds. So for example, if a really important feature, like something critical to your analysis, has, let's say, more than 30% missing values, well, maybe it's better to just remove that entire feature altogether. And I think that highlights something really important. Data cleaning isn't just about blindly applying techniques. It's about understanding the real-world meaning of your data.
Yeah, it's like knowing which battles are worth fighting and which ones are better to just avoid.
Exactly. Choose your battles wisely. All right, so we've got our data in much better shape now.
They're looking good.
It's ready for analysis. But what happens when things start to slow down? Your code is taking forever to run. That's when we need to talk about algorithm optimization. And luckily, the candidate had a lot to say about this.
Let's hear it.
The first thing they emphasize, and this is so important, is pinpointing the bottleneck. Where is the slowdown happening?
Yeah, like finding the weakest link in the chain.
Exactly. And to do this, they had this awesome toolkit of system profiling tools. First up, cProfile. This gives you a high-level view of how much time is being spent in each function.
So you can see, like, which functions are the real-time hogs.
Precisely. Then there's Line Profiler, which zooms in even further, letting you see the execution time of each individual line of code. And then, to round it all out, there's Memory Profiler and Valgrind. These are the memory detectives, helping you analyze how much memory your code is using and where those memory leaks might be hiding.
So it's like having a whole forensic team for your code. You can really get down to the nitty-gritty and see what's going on.
And what's really key is the distinction the candidate made between what they call algorithmic bottlenecks and non-algorithmic ones. So an algorithmic bottleneck, that's an issue with the efficiency of your code logic. Like, you've written an algorithm that's just inherently slow.
It's like taking the scenic route when you could have taken the highway.
Exactly. But then there are non-algorithmic bottlenecks. These are things like slow disk input-output, or I/O, those API calls that seem to take forever, or even database performance problems. And I think this is such a crucial insight because you could spend hours tweaking your Python code, trying to make it faster, when the real problem lies outside your code.
Yeah, it's like trying to fix a flat tire when the real issue is the engine is sputtering.
Precisely. You're focusing on the wrong thing. And the solutions the candidates suggested really reflect this understanding. So for those non-code bottlenecks, they suggested things like asynchronous processing and batch operations.
Oh, yeah, those are good strategies for making things more efficient.
They are. And they allow you to handle those I/O operations and API calls more gracefully. Basically, you can let other tasks run while you're waiting for those slower operations to finish.
So it's like multitasking, right?
It is. And then for database issues, they mentioned some tried and true optimization techniques. First, examine the query execution plan. This basically lets you see how the database is actually processing your query, and then add indexes to speed up data retrieval. It's like having a well-organized filing system. And finally, refactor those poorly written queries. Sometimes just cleaning up the code can make a huge difference.
It's like decluttering your code.
Exactly. Make it neat and tidy. And then they talked about parallelism.
Ugh, parallelism. That's where things get really powerful.
It is. It's about breaking down those big tasks into smaller chunks that can be run simultaneously. And they mentioned the importance of understanding the dependencies between different parts of your data, like which parts need to be done in a specific order, and then using Python libraries like multiprocessing and concurrent.futures to actually implement the parallelism.
So it's like having a team of workers instead of just one person trying to do everything.
Exactly. You're leveraging the power of multiple cores in your computer.
Now, to make this all a bit more concrete, the candidate gave this really interesting example of deduplication.
Oh, yeah, that was a good one.
They talked about how they started with a nested loop approach, which, if you know a bit about algorithms, you know that has a time complexity of O and
We go notation, yeah.
meaning that the time it takes to run the code increases quadratically with the size of the data. Not good.
Not good at all, especially when your data starts to grow.
Yeah, exactly. But then they optimized it to use a Python dictionary, which brought the complexity down to ON. That's a huge improvement, especially as the data set grows. But there's a little twist in this story, wasn't there?
Oh, yeah, there was a catch. And this is where we start to delve a bit deeper into the inner workings of data structures. The candidate mentioned something called hash clustering, caused by those sequential integer IDs. So imagine you've got a bunch of IDs, like 1, 2, 3, 4, and so on, and you're using a simple hash function to put them into a hash table. What can happen is that a lot of those IDs might end up in the same bucket, same location in the hash table.
And that's not good, right? Because you want things to be spread out evenly.
Exactly. You want those keys to be nicely distributed. But when you have this clustering, you end up with some buckets that are jam-packed with items, while others are practically empty. And that slows down lookups, because now you have to search through these long lists within the crowded buckets.
So it's like having a bunch of people all trying to squeeze through the same narrow door. It creates a bottleneck.
Exactly. And the candidate's solution to this was really clever. They started by checking the load factor. That's essentially a measure of how full the hash table is.
So like how much space is left.
Yeah, exactly. And then they monitored how evenly those keys were distributed across the buckets using histograms. Histograms are great for visualizing distributions. And if they saw that the distribution was all wonky, indicating either a bad hash function or too many collisions, they experimented with something called open addressing.
Open addressing, that sounds interesting.
It is. It's basically an alternative way of finding an empty spot when a collision happens. You've got techniques like linear probing, where you just keep looking at the next slot in the table until you find an empty one. And then there's double hashing, which uses a second hash function to calculate a different offset. And on top of that, they implemented dynamic resizing.
Ah, so the hash table can grow if it needs to.
Exactly. As the load factor gets close to a certain threshold, usually around 0.7 to 0.8, the hash table automatically expands, making more room for those keys. And this helps maintain that efficient, average case O1 lookup time that makes hash tables so awesome for so many tasks.
So they're really thinking about performance optimization at a deep level.
They are. And it nicely sets us up for the next part of the interview, which was all about the ins and outs of hash tables.
Let's get into it.
So one of the fundamental challenges with hash tables is, as we just talked about, those collisions. It's when different pieces of data end up in the same bucket.
Yeah, like a cosmic coincidence, but not a good one.
Right. And the candidate mentioned chaining as a common way to deal with this. Chaining is where each bucket in the hash table doesn't just store a single item. It actually stores a linked list of all the items that have hashed to that same bucket.
So it's like a little chain of items all hanging off the same hook.
Exactly. But the problem is, if those chains get really long because of too many collisions, then the time it takes to find a specific item increases. It's like searching through a long, messy list.
Not ideal.
Not ideal at all. So the candidate emphasized the importance of monitoring those collisions and taking steps to address them.
So how do you keep an eye on things? What are the warning signs?
The key metrics they mentioned were the load factor, which we've already talked about, and the variance in the lengths of those bucket chains. You want those chains to be roughly the same length. And to visualize how many items are in each bucket, they suggested using histograms. It's a really practical way to see if your hash function is doing a good job of spreading those keys out evenly.
It's like taking a snapshot of how organized your hash table is.
Precisely. And if that histogram starts to look lopsided, if you see some buckets that are way too full, that's a sign that you might have a problem. Either your hash function isn't doing a good job, or you just got too many collisions. And in those cases, the candidate reiterated those alternative collision resolution methods we talked about earlier, like open addressing. And again, they emphasized the importance of resizing the hash table when it gets too full.
So it's all about staying ahead of those potential performance bottlenecks.
It is, keeping things running smoothly. But now let's imagine a scenario where the stakes are even higher. Think millions of transactions per second.
Wow, that's a lot of data.
It is. And your trusty hash table, it's starting to become the bottleneck. So what do you do? Well, the candidate had some really cool solutions for these high concurrency situations. First up, they talked about concurrent data structures. These are data structures specifically designed to be accessed by multiple threads simultaneously.
So they're built for speed and efficiency in these multi-threaded environments.
Exactly. And they mentioned things like concurrent skip lists, which are great for ordered traversal. You can imagine them like a sorted linked list, but with these clever shortcuts built in. And they use fine-grained locking to allow different threads to access different parts of the data structure at the same time.
So it's like having multiple lanes of traffic instead of everyone trying to squeeze through the same single lane.
Exactly. And then they mentioned lock-free hash tables. These use techniques like sharding or lock striping to break the hash table into smaller, independent chunks. And that reduces contention between threads, because now they're mostly working on their own little piece of the data.
So it's all about dividing and conquering, spreading out the work.
Exactly. And then, to take things to the next level, they talked about distributed systems. Imagine using something like Redis cluster with consistent hashing.
So now we're not just talking about multiple threads, we're talking about multiple servers working together.
Exactly. You're spreading the data and the workload across a cluster of machines, which lets you handle truly massive amounts of data. And then, on top of that, there's the strategic use of caching layers. Tools like Memcached or Redis can act as these super fast temporary data stores sitting between your application and your main database.
So they're like a shortcut for accessing frequently used data.
Exactly. And the candidate discussed different caching strategies, like read-through caching, where the cache fetches data if it's not already there, and write-back caching, where writes are made to the cache first and then later flushed to the main database. And they emphasize the importance of cache invalidation, making sure that you're not serving up stale data. You can use techniques like time to live, TTL values, or event-driven triggers to keep the cache fresh.
It sounds like there's a lot to think about when it comes to caching.
There is. It's not a one-size-fits-all solution. You need to consider the specific demands of your application, whether you need ordered data, the pattern of your data access, and how important consistency is.
It's like choosing the right tool for the job.
Exactly. All right, so we've optimized our data handling, we've fine-tuned our algorithms, but even in the best designed systems, things can go wrong. Bugs happen.
Yeah, bugs are a fact of life in software development.
They are. So the next part of the interview is all about debugging complex systems. And right off the bat, the candidate stressed the importance of two things: reliably reproducing the issue and detailed logging.
Seems obvious, but why are those so critical?
Well, If you can't consistently make the bug happen again, it's like trying to solve a mystery without any clues. You're shooting in the dark. And detailed logging, especially setting Python's logging level to debug, that's like turning on all the lights in the room. It lets you see what's happening step by step. And you want to log things like the execution flow, the state of important variables, timestamps, and even thread identifiers, especially in those tricky multi-threaded applications.
So it's like leaving a trail of breadcrumbs so you can retrace your steps and figure out where things went wrong.
Exactly. And beyond logging, the candidate mentioned some essential debugging tools. For native code, like C++A, there's GDB and LLDB. These are powerful debuggers that let you step through the code, inspect variables, and really understand what's happening at a low level. And for Python, there's the trusty PDB debugger. Sometimes you just need to get in there and see what's going on line by line.
Yeah, sometimes you need to get your hands dirty.
Exactly. But what's particularly relevant for complex systems is their mention of tools specifically for multi-threaded and distributed environments. One of these is Thread Sanitizer. This is a lifesaver for detecting race conditions.
Race conditions, those are tricky.
They are. It's where the order of operations in different threads can lead to unpredictable and often very subtle bugs. And Thread Sanitizer can help you find those nasty little problems. And then there's Zipkin.
Zipkin, what's that all about?
Zipkin is a tool for distributed tracing. It lets you follow a request as it travels through a distributed system, like a microservices architecture. You can see how long it takes at each step, where it goes, and if there are any errors. It's like having a map of your entire system.
So it's like having a GPS tracker for your code.
Exactly. And the candidate also highlighted the importance of replicating the environment where the bug occurred.
Yeah.
If you can't reproduce the bug consistently, it's very hard to fix it.
Makes sense.
And they mentioned Docker as a great tool for creating consistent and reproducible environments. And then there's mocking.
Mocking, that's a technique for simulating parts of your system, right?
Exactly. You can use libraries like unitest.mock in Python to create mock objects that behave like your real dependencies, but in a controlled way. And that lets you isolate different parts of your system and test them independently.
So it's like creating a simplified version of your system so you can focus on just the part you're interested in.
Precisely. And to really bring these ideas to life, the candidate shared a really challenging debugging story. It involved data corruption in a multi-threaded application.
Oh, data corruption, that's never fun.
It's not. And they started by doing what any good debugger would do. They gathered evidence, they added extensive logging to try and understand the sequence of events that led to the corruption. And their initial hunch was that there was a problem with how locks were being used to protect shared data.
So like a synchronization issue.
Exactly. And to confirm their suspicions, they turned to Thread Sanitizer. And sure enough, it flagged a race condition, specifically related to reacquiring locks within nested functions.
So it was a subtle bug, but with potentially serious consequences.
It was. And what's really impressive is that they were able to pinpoint the root cause. They were using a standard threading lock, which is not reentrant. That means you can't acquire the same lock twice from within the same thread. And their solution was to refactor the code to use threading lock.
A reentrant lock.
Exactly. And that solved the problem. But they didn't stop there. They went through a rigorous verification process, running integration tests under peak load, testing in containerized environments that mimicked their production setup, and even using distributed tracing with Zipkin to monitor those inter-service calls. They wanted to be absolutely sure that their fix was solid and didn't introduce any new problems.
So they were really thorough in their approach.
They were, and I think this example really highlights the importance of not just knowing the tools, but having a strong analytical mindset and being really thorough in your debugging process.
Absolutely. And speaking of mindset, the last part of the interview touched on some of those essential skills and attitudes that really make a difference when you're dealing with these complex technical challenges. It's not just about the technical knowledge, right?
It's not. The candidate stressed the importance of rigorous analytical thinking, being able to break down those big, hairy problems into smaller, more manageable pieces.
So it's like having a good problem-solving strategy.
It is. And then there's that meticulous attention to detail. Those little things can make a big difference, especially when you're dealing with complex systems. And they also talked about the importance of continuous learning. Technology is always evolving, so you got to stay curious and keep learning new things.
Yeah, you can't just rest on your laurels.
Exactly. And then there's using data to drive your hypotheses in your testing. It's about being methodical and data-driven in your approach. And finally, they mentioned the importance of thorough documentation. Documenting your code, your decisions, your thought processes That helps not just you, but your entire team.
It's like leaving a map for others to follow.
It is. And the example they gave of using systematic profiling and flame graph analysis to visualize performance bottlenecks, that really showcased this methodical approach. It's about collecting data, analyzing it, and using that to guide your optimization efforts.
And the candidate also talked about the importance of collaboration, right? Especially in larger teams and organizations. It's about working effectively with other teams, like those site reliability engineers or SREs, the database administrators or DBAs, and the DevOps engineers.
Absolutely. Breaking down those silos and sharing expertise, that's so crucial for solving problems quickly and effectively. The example they gave of troubleshooting latency in a distributed system by working closely with the SREs, that was a perfect illustration. They reviewed logs together, analyzed network metrics, and even used Zipkin to trace those requests through the system. And by working together, they were able to find the root cause and solve the problem much faster than they could have on their own.
So it's like having a team of detectives all working together to crack the case.
Exactly. And it's not just about solving the immediate problem, it's also about shared learning and continuous improvement. When you collaborate effectively, everyone learns from each other and the whole team gets better.
So, to recap this deep dive, we've explored the essential steps in data cleaning, the strategic thinking behind algorithm optimization, the intricate world of hash tables, the powerful techniques for debugging those complex systems, and the foundational importance of a strong technical mindset and effective collaboration.
It was a whirlwind tour, wasn't it?
It was, but I think we managed to distill a lot of really valuable insights from that interview. It's like we've given our listeners a shortcut to understanding these often complex technical domains.
And hopefully it sparks some new ideas and approaches for them to try out in their own work.
Exactly. So, as you're thinking about all of this, I want you to consider a complex technical problem that you've encountered recently. Maybe it was a particularly stubborn bug or a performance issue that just wouldn't go away.
The kind that keeps you up at night.
Yeah, those ones. And think about the techniques, the tools, the approaches we discussed today. Which ones might offer a new perspective on that problem? Could they help you find a better solution? We encourage you to explore these ideas further and see how they can apply to your own work.
And remember, the journey of technical learning never really ends. There's always something new to discover.
And we'll be here to help you along the way. We've got more deep dives planned, all aimed at bringing you valuable technical knowledge in a clear and engaging way. So stay tuned, and we'll see you next time.